Start again. All right. The next part of today's lecture will be on what is called Fourier optics. It combines optics and looks at it from the perspective of a Fourier transform. I assume that you know what a Fourier transform is. So, like to give you an intuition or give you a basic idea, so any wave, any function in general can be thought of as a sum of sines and cosines or exponentials, oscillations of different frequencies. Okay, so what a Fourier transform says is that any wave or any function can be thought of as a combination of sinusoids of one frequency, another frequency, another frequency. You add these different frequencies together in different proportions, you can construct any general function or any general wave. Okay, that's the essence of what the Fourier transform is about. How much of this function should you take? How much of this function should you take? How much of this oscillations, sinusoid should you take? That is the Fourier transform of this signal. Okay, add some 1 unit of this plus 2 units of this plus 0.5 of this plus so on and so on. And that sequence of numbers for different frequencies is essentially the Fourier transform. That's one good way to understand the Fourier transform. It has some equation, something, but so what we are saying in essence in the Fourier transform is that take this e to the j 2 pi nu t. What is this? It's a complex exponential. Think of it as a sine and a cosine. Let's consider the cosine just for now. It's a cosine of some frequency. Okay. Add some amount of that frequency plus another amount of a different f of nu 2 e to the j 2 pi nu 2 t. Add this amount of the second frequency, this amount of the first frequency, plus this amount of the third for another frequency. How much of this frequency is basically the Fourier transform. The Fourier coefficients are essentially the Fourier transform. So that's the way to think about the Fourier transform. Is this have you seen this before? Is this basic idea clear to you? Raise your hand if you have seen this idea before. Excellent. That's good. Good, because I can go a bit faster on some portions. Okay. So it turns out that there is a two-dimensional version of a Fourier transform. Just like this, what I showed you over here at the top here. This is a one-dimensional version of the Fourier transform. You can take any image and think of it as consisting of sines and cosines of sinusoids of different frequencies in different directions. Okay, a linear combination. How much of this, how much of this, how much of this do you add? That is the two-dimensional Fourier transform of any signal, any image. Okay, so if you do any course in image processing, you might have seen this two-dimensional Fourier transform. Turns out that this Fourier transform is extremely useful in optics to understand wave optics and wave phenomena. So I'll get to how that is in the next couple of slides. Okay, so the basic idea here is that any wave can be thought of as a combination of plane waves. So each plane wave is kind of like a frequency. Okay, how is the plane wave a frequency? I'll get to that in just a minute. Let me give you a hint as to why that is the case. Let's say a plane wave is traveling in a certain direction. Okay, so let's say a plane wave is traveling in this direction. If you cut this plane wave along the horizontal axis, if you imagine what it will look like, it will basically look like a sinusoid. this is the period of the or wavelength of the sinusoid. You can cut it in a different direction. Cut it this way. You will have sinusoids of this, the kind of that time or wave of that wavelength. So by cutting a wave, plane wave in different directions, you can actually create these kind of patterns. Or alternatively, another way to think about this is any wave can be thought of as a combination of plane waves. Each plane wave is a sinusoid and with in a different direction. So this is what's called the plane wave decomposition of any general signal, okay, or any general wave. So if you have u of x, y, z, which is of this form, this is a plane wave. So what we are essentially saying is that this arbitrarily shaped wave can be thought of as some amount of this plane wave plus, in other words, this wave with a certain amplitude, this plane wave with a certain amplitude and phase, this third plane wave with another amplitude and phase. You add up this plane waves which are going, each plane wave, what is different between one and another plane wave? It's going in different directions. So plane wave going in one direction, plane wave, add that plus to an like twice the plane wave going in a different direction, plus say 0.3 times plane wave going in a third direction. You add up all these plane waves, you get a certain shape. You can, any general wave can be thought of as a linear combination of plane waves. And what is the connection between this plane wave and this? If you write the equation for this wave, and if you take the Fourier transform, it will tell you how much the coefficients, Fourier coefficients will tell you how much of this wave, how much of this wave, how much of this wave are present in that particular wave, or how much you should add of each of these plane waves to give you the overall general wave. Okay, so this is the essence of what's called Fourier optics. Okay, and this works because this is a property of the Fourier transform. You might have seen it in the context of linear systems. Because optics is a linear system, like all the properties of Fourier transforms and everything, because it's also the optical system is also a linear system. Therefore, all the Fourier properties also hold in this case. Okay? So let's say you have an input wave which has this shape. It goes through an optical system, and you get an output. The input-output relationship can be like kind of, this is like a signal, right? Like, so a signal is coming in, it goes through a system, signal is coming out. So this can be thought of as a linear system. And all the, like, when you studied linear systems, you thought of transfer functions, the impulse response, or and all these kind of things, convolutions. If you remember all the things that you discussed and studied in your linear systems course, everything is true here, except for this is in 3 dimensions. So the additional complication here is that it's in 2 or 3 dimensions. That's like that's the, in this case, you have to decompose it like in 3-dimensional space. In fact, in 2 dimensions, and then along the z dimension. So so we'll get to exactly how to do that, but I just wanted to give you the big picture idea of how. So everything that you have learned can be directly applied to optics. Whatever your linear system can be applied to optics, except for the actual like dimensions of space. Okay. So for example, in optics, this is called as the sinusoid in 1 dimension becomes what is called a spatial harmonic function or spatial frequency function. So you have in time you have when you say frequency, it's a function of time, right? But this is what is called spatial harmonic or spatial frequency. So spatial frequency is basically So if you have a picture, so this is one spatial frequency. This is a, sorry, I'm not drawing it well, but this is another spatial frequency. This is a different spatial frequency. So this is a low frequency, this is a high frequency, this is a somewhere in between. So the spatial frequency. This has, of course, there is a frequency and there is a direction to it. Meaning, you can have different. You can have different directions for the same value of frequency. There can be x, they can be, there is a like they are vectorial. So they have different directions in which the frequency is calculated, and these are called spatial harmonic functions, and let me show you a picture which will probably make it easier for you. So let's say this is a plane wave traveling in this direction. If you take a cross section of this, like cut the plane wave in a specific plane, this basically the projection of this on this plane. So basically it's a k vector. K vector, you project it along one axis, right? So that will be, let's say, vector kx. Okay, so that will be what you see on the plane. Okay, so the overall k vector is projected on the kx axis, the ky axis, and the kz axis. So that's so the three, these are the kx is the spatial x frequency, ky is the spatial y frequency, and so on. Okay, so that's in our class we'll think of them like sort of the spatial frequencies will be nu x. So the vector nu is the overall vector, and this consists of nu x, nu y, and nu z. So that's the notation we'll use. Using the right notation happens to be important, because otherwise you'll miss a lot of factors. This notation happens to be very useful in optics. Okay, so basically this is this is the x spatial frequency. You can in this one you can also have the y direction, the y spatial frequency, and the z spatial frequency. So the plane wave can be thought of as the kx vector, ky vector, kz vector, or the nu x vector, nu y vector, and nu z vector. So let me show you how this is useful in understanding, say for example, a diffraction grating. Okay, so now what is it that you can understand about so if in the for those of you who have seen in a few slides ago, I showed you that a plane wave is incident. A grating will split the light into different directions, right? From this perspective, let me show you another way to think about the same phenomenon, what happens in a grating. So this grating can be thought of as a sinusoid of a certain frequency along, say, the x-axis. Okay, a plane wave traveling along the z-axis is incident on this grating. The grating itself is is a sinusoid along the x-axis. What the grating does essentially is adds to this plane wave. It adds that kx frequency. So what was 0, just kx and ky were 0, kz was the direction of travel. So it was traveling along the z-axis. It increases the frequency to kx. So it changes the direction of the direction vector. How much does this so what is this angle? What is the direction in which the light has changed? So what direction does the light go after it goes through the grating? It increases the momentum, or changes the direction by value of equal to the spatial frequency. It adds the spatial frequency to the x direction. And that's the way to think about gratings. It doesn't make sense. Let me pause here and see if you understand what I'm saying. Any questions? The spatial frequency, so let me draw this. So you have a vector k which is along the, like, if your x, y and z axis. This is traveling along z axis. After it goes through this grating has a spatial frequency along the x axis, so it changes the direction. This new vector k1 is such that this kx, there is a kx1 and then kz1 component. So this kx1 is the same as the spatial frequency of the grating. Okay. So the grating is when you have a grating, it's like you have a piece of glass. You have drawn some, like, crudely speaking, you have drawn some lines, right? So let's say it's like you have drawn some lines on it. So that is equivalent to a sinusoid. Like, I'm making an approximation here, but so this is like a sinusoid. The grating is like a sinusoidal pattern on glass. Okay, and that sinusoid has a spatial frequency, and it adds that spatial frequency, imposes that spatial frequency onto the light, and therefore the light changes direction because there is a change in the spatial frequency. So the spatial frequency changes, therefore the light changes direction. And that's how to think. That's the Fourier optics way of thinking about gratings. Okay, and you can also imagine what happens when you have one wavelength and another wavelength. If it's the same spatial kind of, the same pattern, like it depends on. There's a lambda dependence as well, and therefore different. Even though it's the same grating, different wavelengths will get, because there is the angle that the light comes out depends not only on the spatial frequency, it also depends on wavelength. For different lambda, the direction of light will be different. According to if you look at this equation here, it says that there is the spatial frequency of the grating. Additionally, there is the wavelength of the light. So if white light is incident, which has red, orange, yellow and all that, the red light will go in a different direction because the spatial frequency of the grating is the same, but the wavelength is different, and so therefore the direction of all the different wavelengths, each wavelength will be going in different directions. Mm-hmm. 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 Sure, that's correct. So that is because the grating, like this, is a purely sinusoidal grating. It's called what's called a phase grating. So in a grating, so a rectangle, if you think about a Fourier, if you take a Fourier transform of square wave, it consists of multiple sinusoids, right? Each sinusoid will give a different direction, and therefore you will have multiple orders of direction even for a monochromatic wave. You understand what I'm saying? So basically, the grating can be thought of as, if a square wave grating can be thought of as combination of different sinusoids, and each one of these sinusoids changes the direction in different, and so there's the first direction because of the first frequency, second direction because of the second frequency. The DC means it's continuing going straight, nothing is happening, and so on. And that way you have, even for a single wavelength, so this is for a purely sinusoidal grating, but most gratings are not sinusoidal, but they're kind of, most people make gratings. They take a piece of glass like draw lines on it at some specific period, like kind of essentially etch some like glass out at uniform spaced intervals. That creates a square kind of a pattern. The square is nothing but a sinus, like sinusoids of it consists of multiple sinusoids. Each sinusoid gives you a different direction. Therefore, a grating like actually it gives you different direction, like transmits lights in different directions. That's another additional complication. For any single one grating, it changes direction by proportional to the spatial frequency of that grating. Okay. Yeah. So there is a formal kind of rigorous way of figuring this out. So basically, you the like any image or any wave pattern along xy can be decomposed into its Fourier spatial frequency components, and you add up all the spatial frequency components, you will get the original wave, right? So therefore, like yeah, so this is the definition of the Fourier transform. In our case, you have u of x, y, and z. You have the spatial frequencies along xy, and then propagates along z. One thing in optics is that xy is different from z, meaning if typically the kind of general rule of thumb is you assume that light is traveling along the z direction, okay, and so the direction in which it's traveling is the properties are different from perpendicular to it. In a wave plane perpendicular to the traveling direction, the wave is like that's say you put a detector or a screen or something, that's how you make a measurement. So those are kind of treated differently mathematically speaking. So the xy is this, and then the z is over here, okay, and this because you have the relationship k vector k is kx consists of kx, ky, and kz. It means that, like, if you take the magnitude, it's equal to square root of kx square plus ky square plus kz square. So there is and therefore, if you want to find kz, so kx, ky, kz are not independent variables. If you know k and if you know kx and ky, kz is completely determined. So therefore, kz is square root of k square minus k x square minus ky square. Or in terms of nu x and nu y, it's this relationship. So there are three independent numbers, but there are k, kx, ky, kz. So there are four variable names. So kz is typically defined in terms of kx and ky. You think of kx and ky as the independent variable, and kz is the direction vector along a z. Yeah. So yeah. So if you have a plane wave incident on any general, like some object, which is assume it's thin for now, and it has this pattern f of x comma y, the plane wave will get decomposed into different plane waves, so multiple plane waves, and this plane, how much of different plane waves come out, one plane wave goes in, multiple plane waves go out, how much of each plane wave is present, that is the Fourier decomposition of fx and fy. That's essentially what we are saying. So take for example, you have this kind of an object, light comes here, light gets scattered in or kind of transmitted and comes out on the other side. So a plane wave is coming in and some kind of a wave is coming out after it goes through this particular object. What is the shape of this wave after it goes through the object? You can take the Fourier decomposition of this object, and that will tell you all the wavefront of the light coming out at the other end. What are the different plane waves coming out at the other end? So if you have a slightly different pattern here, this is a sinusoid imposed, everything will shift by that amount. Okay, so it's changed, like it's like take the object and then put a grating on in front of it. So it goes through that, it gives you the decomposition. What happens when you have plane waves going through a grating? They all shift direction, and all of them go in shift and go to in a sort of what was going in this direction. The same wavefront is just basically transferred to this extra. The direction changes by a fixed amount because of the grating that you put on top here, which has nu x naught as the spatial frequency of the grating. Okay. And so you can choose the shape of this object here and make light do a lot of different interesting things. What do I mean by that? If you make, say for example, this kind of a pattern here, draw this or print or kind of make a object which has this shape pattern, then a plane wave coming in can be made to focus light to a point. So you can actually make a device such that you create a pattern on this on this plate or on this surface, and it after the Fourier transform of this is a spherical wave, and therefore the spherical wave will converge to a point. Okay, so this is what's called a Fresnel plate. So normally, if you have plane wave incident, you have a lens, it converges to one point, right? That's the simple way of thinking about lenses. What I'm saying is that instead of a lens, you can have this plate where it's like there is a certain pattern on it, and that pattern will also do the same thing as a lens, which is converge light a single point. So this is all in fact called a Fresnel lens, and the scientist who came up with it, this was in fact they did not understand Fourier optics then, but basically the concept was figured out a long time ago, and making this in fact so what is the advantage of this? So let's say so this was used by Fresnel in lighthouses. So basically, let's say you have a lamp, and there is what a lighthouse is. So in an ocean, at the beach, basically there's a tower where there are ships, and you at night time you have this lamp, and so that far away where the coast is, the ships can see. So they needed something which is where there is a lamp, and they wanted to, instead of a lamp emitting light in all directions, they wanted to put a lens so that it focuses and goes towards the ship, towards parallel to the surface of water. So they put a lens in front of the lamp. So in order to, so these are giant towers. The lens would be the size of from 6 feet or 8 feet kind of lenses you had to make. So that you could. So that requires such a big amount of glass, right? Making that giant piece of glass was extremely costly and difficult, and would break easily and so on. So what Fresnel figured out was, instead of having this giant blob of glass which is in the shape of a lens, you could make this thin plate where you make this pattern on it that would essentially focus light as though there is a lens, and that was one of the practical uses of this what's called a Fresnel plate. Okay. So yeah, any questions? Sure. This one? You could. This is just an example. You could have x and y component. If you have x component, then the direction will change towards x. If you have y component, it also change towards y. Do you get what I'm saying, or maybe I misunderstood the question? Here? No, so in this particular example, this greeting is only along x. so this is y, right? So it's like, so basically it's like this. It's parallel to like the y-axis. Lines are parallel to the y-axis, so there is no component along y. Yes, the x-axis. So if you cut it, it's three-dimensional, like it's a picture in 3D, so it's hard to draw it exactly. But it's the grating is only along x-axis, not along y. Okay. Okay. So so basically this so if so the next question is like if you know that light, a wave is in a certain plane, you know the equation for a wave in a certain plane, how, like, and then you want to know what happens as light travels, what is the shape of the wave. So in ray optics you assume that you have a certain wave like, or you have a certain ray and the ray goes in a particular direction, right? If you know what are the rays here, if you know the direction, you can figure out what the rays are in here. But in wave optics, the problem is that, let's say the wavefront is like this in this plane. As it travels, it can change shape, right? So the question is, if you know the wavefront in this location, what is the wavefront at this location? So how do you figure out what happens as the wave? So because the wave spreads, so you need a way, you need some kind of like some method to figure out how does the wave travel from one plane to the other. Okay, because the linear system, you know, like it's as though this is the input wave, the output wave, it's going through a system, and so the question is, what is the input output relationship? In other words, what is the transfer function for that system? And in this case, the system is just traveling of light in air or free space. So in other words, what we are saying is, what is the transfer function of free space? So to state it in a different way, if you know the wave, shape of the wave in one plane, what is the shape of the wave in a different plane after a few, like say 1 meter away or something of that sort? So what is the wave shape? If you know the shape here, what is the shape over there? And so if you know the transfer function, then you can take this wave, multiply in the Fourier domain, you multiply it by the transfer function, and you get the output input. So in the Fourier domain, what happens in linear systems, you have an input signal, take the input signal, multiply with the transfer function, you get the output, y equals hx, right? If you remember your like in the Fourier domain, y equals hx, it's a multiplication in the Fourier domain. So if you figure out h, which is the transfer function, then you can figure out how the light travels. Okay, so that's essentially what we are doing. So what we need to do is find the two-dimensional transfer function of free space. And so this happens, this is like, the short answer is, this is the transfer function. Okay, so the e to the j 2 pi d is the distance here, times, like, what is this? This is just the, like, the 2 pi with this is just kz times d. Okay, so basically what we're saying is e to the minus j kz times d. That's essentially the transfer function of free space. Let's look at the implications of this. So basically, so if you have just a plane wave in a certain direction incident, and this plane wave is traveling here, it travels a distance d. Then, like, if you look at it at a different plane, all that has happened from here to here is, it has accumulated phase. If it's one plane wave, it has accumulated phase. So this is a certain spatial frequency. This is the same value of spatial frequency, except for it shifted a little bit, or his phase has changed a little bit. So this plane wave has gone here. So the phase here has changed, and it has So all that has happened is it has accumulated phase, and therefore by a as it travels in space, and therefore for a single plane wave in a certain direction, the magnitude of the frequency is the same, but it has phase of this wave has shifted, and that's the relationship. So that is essentially what we mean by the transfer function of free space. Any questions? Okay. So this transfer function, so this is the equation, 2 pi d times this, right? So we can sort of take the lambda outside, you get lambda by d, and then so divide you can do lambda by lambda square times this, and therefore if you take a Taylor series expansion of this, this is of the form 1 minus theta square to the power half, and the 1 minus theta square over 2 is the Taylor series approximation, first order Taylor series approximation, right? So the first order, if you do the first order Taylor series approximation of this transfer function, you get something of this sort, which is h naught, which is a constant, times e to the j 2 pi d lambda d nu x square plus nu y square. So this is a what does this look like? It's a parabolic shape in the Fourier domain. Okay, in the Fourier domain, this looks like a parabolic shape, and this approximation. So going from this, so this is the most general transfer function transfer function for free space is this, but an approximate version is where you make you use the Taylor series and keep only the first order Taylor series, and what you end up with is this parabolic shape, or x square plus nu y square kind of a shape. Okay, so this is the nature of the transfer function, and so this is called the Fresnel approximation. Yeah. So it's a circle in nu square. If you say nu x square plus nu y square is constant, that is a parabola. But just like I showed you, in one direction it is a circle, in the other it is parabola. Okay, so f of nu x nu y. This is the Fourier decomposition of this plane wave. Okay, so how so whenever you think of linear systems, if you know the signal in this one, if it goes through a system, to find the output. So if in one dimension, what happens? If you remember your linear systems, if you have y of t equals h of t convolved with x of t, right? If x of t is the input and h of t is the impulse response, then the output is the convolution of the input with the impulse response. Similarly, in two dimensions, you have y of x comma y is the convolution of its two-dimensional version of that. So basically what we are saying is that the output gxy, the wave shape of the wavefront at this one location is basically the convolution of the input and the impulse response. Okay, so if you substitute for h of nu x nu y, you get this equation, and so g of x is input convolved with the impulse response, and therefore you get this kind of an expression. So this looks a bit complicated, it looks a bit long, but the important thing here is the ideas present in this. So what As long like one good thing about optics is that like you don't need to worry about some of these equations because you can think in pictures. If you can understand what this means, so this is a spherical wave or this is a plane wave, it's kind of, you can think of it as a combination of plane waves, combination of spherical waves, and so on. So it makes it much easier to understand a lot of optics because you can think in terms of pictures. I'll show you the pictures that I'm talking about. So one kind of one way of thinking about it is in terms of Huygens, what is called the Huygens principle. What we are essentially saying, what we are saying here is that take any dot here. This is emitting a spherical wave. Take another dot which is emitting a spherical wave. It travels with this equation. Its amplitude is reducing as proportional to 1 over r. Its phase is increasing. Add up the contributions of these plane waves and then another point. Take every point here, like you have spherical waves. Add up all the contributions of these spherical waves, and the output at any point is that. That's essentially this equation here is essentially saying that. Okay, in pictorial terms, this equation is saying take a point x prime comma y prime, propagate it as though it's a spherical wave, add up the contributions of all these spherical waves at the other end. Adding up means integrating. Okay, add up for every dot here, add up the values of for every x prime y prime. So every point here, add up all the contributions of all the different spherical waves at this plane, and that is the wavefront at the other end. Okay, that's essentially what this equation is saying. Yeah, sure. So that's an interesting question. So the impulse is essentially the spherical wavefront, like a dot. So let's see, what is an impulse in 2 dimensions? It's a dot. So every dot, so in 1 dimension you have an impulse, right? A dot is an impulse. And how do you make a dot practically? Let's say you have a piece of paper, make a small hole in it and shine light on one end. A small amount of light comes out to the other end, a dot of light. That's an approximation, but you get what I'm saying. A pinhole is a point, infinitesimally small point in principle. A dot is basically a 2-dimensional impulse, and the response of that impulse is the spherical wavefront. So one dot gives you the spherical wavefront is the impulse response. Next, another dot. Add up all the dots, a weighted combination of all the different dots. That will give you the wavefront. That is Huygens Fresnel principle. That's basically the idea. You get what I'm saying? Okay. Yeah. So this leads us to what's called the optical Fourier transform. Believe it or not, optics, light, real world objects do Fourier transforms all the time. Okay, that's essentially what I will show you in the next few slides. Okay, so act of propagation of light results in a Fourier transform. It may be unbelievable right now, but bear with me, and in the next few slides I hope I can convince you that this is actually what's happening, and you can understand a lot of things which previously you did not think of as anything related to frequencies or Fourier transforms or anything of that sort. I'll show you that they are kind of so very closely related to like Fourier transforms in a very fundamental way. Okay, so basically start with the equation that we just got previously. So what was this? Is fx x prime y prime e to the something. So this is a function of this can be written in this uh, we'll write it in in this form. Okay, so this is what's called the Fraunhofer approximation. Let me show you how we get to that. Okay, so x minus x prime can be and y minus y prime can be written as x square plus y square plus 2xy. Like, so you split this, each of these terms, you separate each of these terms. X square plus y square, you keep it outside. Then x prime and y prime. Okay, so now if you take the, so you're integrating as a integrating over x prime and y prime. So xy will be parameters which come out of the independent of x and x prime and y prime. You come get it out. So you have f of x prime y prime e to the something times x prime something times y prime. What is this something? It's f of, let me just write the one dimensional version, e to the j 2 pi something x prime integrated over dx prime. What does this equation look like? F of x e to the j something x, if kxx or fxx or omega x, right? This is the definition of the Fourier transform. And basically what we are saying is that what happens to light is that under some approximations, the field at a certain plane here is the Fourier transform of the field. So if you know the wavefront in one place, the wavefront farther away is proportional to the Fourier transform of the field here. In other words, as light travels, it performs a Fourier transform. Okay, that's really what we are saying. Okay, so yeah, so g of x comma y is the Fourier transform of x. There are some proportionality constants lambda times d, but take the field f of x comma y, take the Fourier transform of that, that is capital F of nu x comma nu y. If you substitute nu x equal to x by lambda d and nu y equal to y by lambda d, then you will get, and then there is some phase factor here, you will get gx gy. Okay, so this is, yeah, so this is one way to think about so this is one way to think about how a Fourier transform actually happen. So this is called this approximation. So this is under a certain kind of, we have made this Taylor series kind of approximation, right? So under this specific approximation, this is what's called the Fraunhofer approximation. Light performs a Fourier transform. Another thing is, even a lens performs a Fourier transform. How do you think about that? So say a light is incident on a lens, so plane wave. Okay, so plane wave is let's think about its incident. Okay, so let's say a plane wave is incident on the lens and it focuses onto a point. Plane wave is, if you think of what is the wavefront, it's a constant, right? What is falling on the lens is a constant. And it focuses onto a dot. Okay, plane wave is a constant. What is the Fourier transform of a constant? Fourier transform of 1. What is the Fourier transform of constant? No. Delta. It's delta of, it's a delta function, right? And what is a delta function in 2 dimensions? A dot, right? So plane wave comes in, it becomes a dot. So it has performed a Fourier transform. Do you see that? Same thing. If you have a lens, if you have a dot on one side, it goes and it becomes a plane wave. Light, if it is at the focus, at the position of focus, it's a dot. A dot travels through the lens, becomes a plane wave, becomes a constant. A dot is a delta function. Fourier transform for delta function is constant, is 1. So if you put a dot on the left side, it becomes a constant on the other side. If you put a constant on the left side, it becomes a dot on the other side. Sure. Both the forward and inverse, right? There is a factor of 2 pi, but that's not crucial, right? Both what's the difference between forward and inverse Fourier transform? There's just a minus sign. So if you actually, and like it'll just be, yeah. No. Constant means 1 or some some number. So what I'm saying is, like you have 1, it has a Fourier transform of delta of like f, for example, okay? And if you have delta of x, this Fourier transform, there is I'm ignoring proportionality constant, so please bear with me. Okay, it's some like proportional to 1. So there is 1 over 2 pi and stuff, but you can write it in a way. You see what I mean? So basically what I'm saying is that if you have a lens and you put some object at the position at a distance equal to the focal length of the lens, and at the other side at a distance f, the lens would have performed a Fourier transform of the object. And this is true not just for points or plane waves, it's true for any kind of function, any wave. If you put an image of something and put a lens in front of it, so this is actually a way of computing the Fourier transform. So this is an optical way of calculating the Fourier transform, which at the speed of light, which is faster than any computer can possibly do. Okay, so this is something which is interesting and useful as engineers. Keep this in mind. It could be very useful as we go along. Okay, this is a way of thinking about the optics. It's also a very practically very useful way of. In general, if you have one plane, it at a distance d from a lens, and if you look at a distance f, you put another kind of a detector or a screen over there. There's a plane wave decomposition of all of this, and if you write the equation, if you do the transfer function, it look something like this. And there is this. So the only issue is that for the Fourier transform, there is this x square plus y square by d. There is another phase factor, which is kind of complicating things just a little bit. Okay, but it turns out that if you use a lens, so there is this number d x square plus y square times d minus f. And what we are saying is that if d equal to f, this factor completely goes away. E to the 0 becomes 1. And therefore what remains is the field or the wavefront that you measure on the other side of the screen. If this distance is equal to f, so take a lens if its focal length is f, keep an object at distance f from it. On the other side at a distance f, if you put a screen, then and you may light is incident on this, it kind of creates a pattern, and the light that you detect on the other side will be the Fourier transform of the whatever you put on the left hand side. Okay, so this is interesting and practically very useful, and not just for it's a way of thinking about it. And so a lot of things that you kind of so this is useful in thinking about a lot of optical problems. So let me give you a few examples. Okay, so let's say a plane wave is traveling in this direction. Instead of it traveling exactly along the optical axis, just tilted plane wave, it's incident. So tilted plane wave, what is the, if you put like, what does it look like over here? It will be a sinusoid. It's the kx component which you see on the screen. Like if you put a screen there, you will see a kx component, right? It will be a sinusoid along this axis. So it's a sinusoid of a certain frequency. If you take a sinusoid of a certain frequency, or if you take its Fourier transform, what will you get? A dot, which is a shifted dot. That's actually what. So light focuses to a dot, which is like if it was purely plane wave like this, it would focus here. If it's a tilted plane wave, it would focus to a shifted dot, and the shift is proportional to the spatial frequency at the input. Okay. Okay. In summary, what we are essentially saying is that the complex. So if you take an object and put it at the back focal plane, so the left side, like, so this is called the back focal plane, this is called the front focal plane, like, at a distance f on the left side and a distance f on the right side. So if you put it on the back focal plane and if in front of a lens, and the other focal, like on the other side, basically it's a Fourier transform of the waveform on the left hand side. That's essentially what we are saying. Okay. Any questions about all this? Let me. I'm trying to see if we have time for okay, let me go through the next few slides, and in case I have to stop there, like, I think we are kind of getting close to our time, but let me try to finish this. Okay. So the next is how can we use this concept of Fourier optics to understand diffraction of light. So this is an image of, let's say you have something which is like a shape like a triangular kind of if you shine light on something which has this triangle, like triangular shape, at the edges you see these kind of patterns. The edges are blurred, right? So in ray optics you would think you'll see exactly like a straight edges, but because light diffracts at these edges, you see shapes which are look something like this, and this is the phenomenon of diffraction of light. Okay, so this is essentially what so this is also a consequence of the wave nature of light, and the Fourier optics allows us to understand this quite well. So to give you an example, like say you have a metal or piece of paper, you have cut out a hole, circular hole here, light is incident on it. In the ray optics picture, what do you expect to see far away? Yes, just a circle, which is maybe bigger, slightly bigger, depending on how the light is incident. Could be bigger perhaps if it's a point source on the other side, but basically it should have a shadow. It's kind of like a just a bright circle. But in the wave optics picture, as light travels, it performs a Fourier transform of the circle. What you will see is not a circle, but a ring-like pattern. So what you will see basically is like take the Fourier transform of the wave and the magnitude square of that is actually what you will see. Okay, so yeah, so so basically you will see a circle along with rings. Like what's the Fourier transform of a circle? Does anyone know? Or maybe let's start with the one-dimensional case. Like if you take a cross section of a circle, it's a rectangle. So what is the Fourier transform of a rectangle? Sinc function, right? And if you rotate this and you create a whole two-dimensional version, this will be, it's called a jinc function, Jinc instead of sinc function. It's like a sinc function with kind of ripples on the side, except for circularly symmetry. So that's the two-dimensional Fourier transform of a circle. And in fact, that's exactly what you will see. What you will see is that on this, instead of you just seeing a circle, you will see circle with rings on side, what are called side lobes. So in fact, like you can do this experiment, and actually, if you have a very big hole, it'll like you won't see the diffraction phenomenon. But if the hole is small enough compared to the length of light, then you can actually see these ring-like patterns in microscopy, in all kinds of imaging systems which look at small objects. This is exactly what you will see. And you put, like, if there's a dot in the microscope, you will see ring patterns. In fact, this is used in what is called, the fact that it's like kind of this kind of ring pattern can be very useful. There is a kind of microscope called PALM, palm microscopy, where the basic idea is that, like, if you have one fluorophore, one dot which is emitting light, and you look at it under a microscope, it looks like it shows this blurry circular kind of function, right? Because you know the shape of this like ring pattern, you can figure out the middle of the ring, locate it very well. Even though the spot is big, the circle is big, the center of the circle you can locate it precisely. What it means is that you can, to nanometer precision, you can identify the center of this dot. And therefore, this is used in what is called super resolution microscopy. What it means is, you have a big object and you see this big blob, but you find the middle of this big blob because you know the shape of this kind of ring-like pattern. And by doing that, you can find the middle, which is where the object is located. And by knowing the location of this pattern and constructing a bunch of these kind of ring patterns, by looking at a bunch of these, make them blink, and each time you find a circle pattern, get the dot location, next dot location, next dot location. So you connect the dots and you can get much higher resolution than was previously possible. So this was one of the three ideas that got the 2014 Nobel Prize for what's called super resolution microscopy. This was discovered by a scientist called Eric Betzig, who discovered this. So using this basic idea of kind of this, knowing the shape of this point spread function. So it's a point which it spreads into this shape. So if you know the point spread function, you can figure out where the middle of the dot is. And so this is what's called super resolution microscopy. Similar to this, instead of having a circle, if you have an aperture which is rectangular. What is a rectangular aperture? If you cut it along one direction, it's a square. If you cut it along a different direction, it's another square, which is a square, which is a different shape. Right? What you see along this direction is a sinc function. What you see along this direction is another sinc function. So it's a combination of sinc along x and sinc along y. So again, it's a Fourier transform. That's exactly what you will see if you pass light through a slit of a rectangular cutout of this shape. And yeah, so this kind of Fourier transform is under the Fraunhofer approximation. So what does this is basically only true if when light propagates for a fairly large distance, and this is basically paraxial, meaning you are only considering waves which are going close to the axis of the light. If you think of waves which are slightly farther away, then this is not true. For a lens, it's an exact relationship, but for just light traveling in air, it's an approximation for distances which are far away, not for things which are very close. So if you want to figure out what happens, like when light goes through free space, there is this extra factor of e to the x square plus y square. There is the additional curvature factor which comes in. Apart from the Fourier transform, you apply the spherical curvature to the wavefront, and that's called the Fresnel diffraction. So basically, so you have like a cut, you have a hole in here. So it's kind of, this is the starting point. As it travels, it does this Fourier transform slowly, and you get this kind of a sinc function as you go along. So this is, and if you have a Gaussian at the input, a Gaussian will become spread. So if you remember your linear systems, the Fourier transform of a Gaussian is a Gaussian. So like Gaussians are one of those few functions where the Fourier transform is the same shape as the original function. Why it matters in practice? Most lasers and most things that you make, if it is Gaussian, then it will remain Gaussian as it travels. So it's a very useful kind of, and in fact, a laser pointer, for example, most of the things that are made in lasers and are Gaussian shaped. The beam profile, beam shape is actually Gaussian. That way, as it travels, it continues to be Gaussian, and it's called Gaussian optics. We'll get to that a little later. So basically, a Gaussian will, the width of the Gaussian will keep increasing, and as it spreads, but still Gaussian remains a Gaussian as it travels. Okay, so to summarize, we discussed a lot of things in today's lecture. So as you increase the distance from the aperture, the diffraction pattern is a shadow, essentially like a shadow of the aperture. In the Fresnel diffraction pattern, there is apart from there being a Fourier transform, there is the e to the x square plus y square kind of a term. In the Fraunhofer pattern, it is take the Fourier transform, take the magnitude square of it. Why magnitude square? It's you measure the intensity. So in the Fraunhofer approximation, basically light traveling at a large distance is equivalent to computing the Fourier transform of the field. Okay, let's stop here for today, and we'll build on this and continue how to make instruments, what are the principles of operations of different kinds of optical instruments, how we can use interference to get some images from inside the body in 3 dimensions, or we'll discuss all these questions in the next few lectures. Okay, and that's it. Thank you, everyone. Any questions before I wrap up? Any questions? Yeah. Yes. That's it's very interesting that you say that. I was yeah. So let me get to something. This is something before we started. Just before the break, I showed you this. So there is let's say you have a piece of paper where there are 2 holes. Okay, this one hole creates something like a dot will create a plane wave on that side. Another hole will create another plane wave, right? If you think this as a delta function, this is the second delta function which is shifted from that one. So in linear systems, if you have two delta functions. What is the Fourier transform of this? Cosine. Sine or cosine, right? But right. So what is this? This is a cosine. So if you remember, this is like the Young's double slit experiment from like 11th and 12th, if you remember. So the Young's double slit experiment is basically you have two holes, and what is happening is you're computing it's like two delta functions and shifted delta functions, and when you what happens is that it becomes a Fourier transform of the two delta functions, which is a cosine. The cosine is a fringe pattern, and the more distance there is, the higher the frequency, so on and so forth. Like all you can do all the calculations from Young's double slit experiments. Like as in, at least in the high school 11th and 12th version, you might not have made the connection between like the frequencies or anything of that sort. So like sort of this connects the world of kind of classical optics, which previously people had figured out, to how to think in terms of spatial frequencies, and like what is the connection between like these spatial frequencies and like how light propagates. Yeah. It's a good question. Any other question? All right. Thanks, everyone.